sessions. I hope I'm audible. So in previous sessions we have discussed like mostly thermodynamics in the last two sessions, right? So this session we will finish thermodynamics part, and after that we will do like not characterization but production. How do you produce these nanomaterials, or how do you make these nanomaterials, and then we move on to this part called the properties. So at first we will have for now this session we will have thermodynamics part just a little bit, and then we will move on to the production, or how do you form the nanoparticles. Or nanomaterials, and then we will have the properties, how the nanoparticle properties varies with respect to bulk. Okay, so properties can be many types. We can have what? The mechanical, the electrical, the magnetic. Acoustic will not be it's not a big thing in nanoparticles because the particles are so small, and yeah, you can have thermal, so thermal, mechanical, electrical, magnetic. And acoustic is not very much related to the nanoparticles because for acoustic you need a big material, right? Because the sound waves needs a medium, and nanoparticles are very small. So we do not do, or we do not involve, or we do not go much into the acoustic part, right? So yeah, this will be in the next session, I guess. Yeah, you will maybe most probably next session. So again, many of you have some confusion with the Gibbs-Duhem equation, right? So why do we use the Gibbs-Duhem equation? Because I have seen people like contacting me and asking me, please can you explain more about the Gibbs-Duhem equation? So yeah, so what do you mean by Gibbs-Duhem equation? Now, what do we need for Gibbs-Duhem equations? Right, so why do we care? That's the main point. So for example, if I want to find a relation between the chemical potential, how the chemical potential will change with respect to the composition. Okay, so vice versa, even the composition how can change with the chemical potential. So yeah, for that we need to use the Gibbs-Duhem equation. Now, the one thing about the Gibbs-Duhem equation is it takes the equation first, and then it cancels out whatever the part that wasn't changing in that equation. So what do I mean? Right? So let's say okay. Let's say we are doing at constant pressure and temperature. So my VDT and SDT are 0. Okay, because the temperature and pressure are constant. These are constant, okay? The constant pressure and temperature plus my chemical potential of I dxi plus, let's say 1, or yeah, 1, let's do 1, and mu2 dx2. Okay, so this is my equation. Now I can write my equation like this. I'm just writing it, so it doesn't relate to this here. Okay, I'm just writing it. Now what I'm trying to do is I will differentiate on both sides. Okay, so let's do first mu1 first. So x1 d mu1 plus x2 d mu2. Now let's do for x1 mu1 constant pressure and temperature. Now when you compare this one and this one, this are equal, right? Because that's what we see here. These two are equal, right? So they cancel out. Now what is remaining? Remaining is this guy, which is equals to okay. Now there are many relations here from which you can even derive this. Okay, so one thing about this equation is, so let's say my solution is not an ideal solution. Okay, so let's say this is just a bit off topic, but still you people need to understand, right? So what do you mean by that? So let's say my solution is not an ideal solution, then my chemical potential will be mu naught plus RT log. Now activity comes here. Why activity? Because when it is ideal, my activity will be equals to mole fraction. When it is not ideal, then my activity will be activity coefficient times the mole fraction. We have discussed this. This is for ideal solutions, this is for non-ideal solutions. And activity again may be a function of what? Maybe a function of what? Temperature, again composition, maybe pressure, or any other thing. It can change with many terms. For the interaction parameter, I can even write mu dash some interaction parameter. So it depends on many things. So that's why we use it whenever we deal with non-ideal. Right? Now, so what happens then? Then let's write x1 d mu1 equals to minus x2 d mu2. Okay, nice. Now, how is my chemical potential 1 is changing? Let's write d mu1 will be equals to minus x2 by x1 d mu2. What is my d mu2? D mu2 will be x2 upon x1, and mu naught will go away. So I have only RT ln, right? So it will be RT ln x will be 1 by a a2, and then you have d of a2, right? x2 upon x1 RT. What is 1 by a2? It is activity coefficient of 2 times x2. These two guys will get cancelled. Then all I have is minus of RT upon 1 minus x2 which is d mu. Again I have to do the differentiation with A2, like differentiation of activity. So what happens here? Let's add this, right? So differentiation of activity 2 will be equals to difference. Let's for example, let's differentiate it. So x2 d coefficient of 2 plus activity coefficient times change in x2. Okay. For example, let's say activity coefficient is not changing, or it is constant. Still, it is not an ideal solution. Okay. Let's say it is constant. Then what happens? dA2 will be equals to activity coefficient times dx2. So if I write this here, d mu1 will be equals to minus RT on x1. So the coefficient gets away. D mu1 will be, you will get minus, and you will have 1 here. So right, dx1 upon x2. So if you do differentiation, integration, then you will have a1 equals to mu0 plus RT log x1. Now this is for ideal. Okay. If you take constant, then it will get ideal solution. What about if I didn't take the constant? Then I have to write this whole guy, this whole term. I will have x2 upon 2, then I will have mu2 plus mu2 will get cancelled, then I will have x2. Okay, now dv1 equals to minus RT upon x1 x2 upon r2 plus dx2. Now see, when we do the differentiation, at first this part and this part will turn into RT ln x1. This part will turn into RT ln x1. Now we do not know how this one changes with this guy. So again we have to derive this part. We do not know how the activity coefficient of 2 will change with and chemical potential of 1. So for that what we do is simple. Again we take the Gibbs-Duhem equation, this guy. Now what we do is, let's see, dv1 minus x2. Stop it. So x2 and dmu. Okay. So what is my dmu1? dmu1 is RT 1 by A1 times, so yeah, x2 dmu1 x1 dmu1 plus activity coefficient times dx1, and here minus x2 RT 1 by A2 x2 d coefficient, change in coefficient of activity coefficient times activity coefficient times change in RT will get cancelled. Then I have x1 divided by 1 by A, that will be 1 by activity coefficient, right? And then I have x1 dv1 activity coefficient dx1 minus 1 by activity coefficient of 2 x2 d activity coefficient, change in activity coefficient plus activity coefficient of 2 dx2. Please bear with me, this will be very important, because whenever you do whenever you try to do the chemical potential, if you want to find the chemical potential of 2 nanoparticles or the chemical potential of a nanoparticle, it has 2 phases. Then how do you find the chemical potential of that phase? How does the chemical potential will change? Okay. For that you need to derive this part. Whenever you do more research into it, then you will face this problem. How do you have a relation between chemical potential of phase in a nanoparticle? This will come up when we are dealing with the mechanical properties, thermal properties, or even electrical properties. Okay. So yeah. So what will get cancelled when I multiply with this guy? So I will have dx1. So I will multiply this guy with this. Then first I have x1 d this guy and plus dx1. Same x2 plus dx2, and we know dx1 equals to minus dx2, right? When I substitute here, then d1 plus dx1 equals to, I will multiply minus, now because so dx2 will be minus dx1, right? And there is also minus times minus plus. This guy will get cancelled. So what I have, x1 d gamma 1 by 1, activity activity coefficient minus x2 change in activity coefficient of 2 by activity coefficient. So this is my relation. Now I know this equals to this guy. So if I substitute that thing here, right? So d mu1 equals to minus, so there is a minus, it will get plus let's keep RT outside, okay? So okay, then let's write everything. Let's not confuse ourselves. This one. Let's do already multiplied them up, right? There is no need of writing that here. So, okay, now, and what is this? This guy. I'll just write it here. So, RT x1 minus x1 by 2 the coefficient of dx2. Now again dx2 will be minus dx1, everything is multiplied, plus. So first I have d gamma 1 by gamma 1 dx2. That's it. Now all you need to know how the activity coefficient change, right? So there is no way to do this because it will finally become RTL on x1, right? Because chemical potential equals to a pure, then at some point of x1, and this will become mu of x1 minus mu naught. The only thing that is going to change is this guy. How my activity coefficient is going to change. So for example, if my x1 is 0, what will be my activity coefficient? Activity coefficient will be 0, right? That's it. This is a very important equation for Gibbs doing any type of phase quantification or anything you are trying to do. Now, what is next part? So next part we are dealing with is the melting point. Again, melting point we have derived many times, so there is no, I guess there is no need for doing it again, right? Because we have did for like 2 times, right? We have derived it for 2 times. So it's simple. Whenever you have surface, you have high energy because you have broken bonds. So there is this is like logical way of explanation. You can derive it because you can just refer to the previous lectures. So this is like more simple way of explaining. Whenever you have nanoparticle, you have more number of surface broken bonds. So it is in itself is at higher energy. So all we need to do is supply some amount of energy. That's all. It will melt. So that's why whenever you decrease the size of the nanoparticle, the melting point goes down. It's not even melting point. It's even the phase transformation goes down. Right? Because I can write it. Dg alpha will be equals to V alpha, V change in volume of alpha, V dP, right? Change in pressure, minus entropy of alpha dt, or even in, you do not even have to write this more tough. You can just write the change, right? So delta G will be equals to delta H minus T delta H. What is my delta H? Enthalpy of, like, so for example, alpha is transforming into beta. Okay, so delta H will be enthalpy of beta minus enthalpy of alpha. That is the change in reaction, right? How do you find the enthalpy of reaction? You just do the enthalpy of reactants minus enthalpy of products, or enthalpy of products minus reactants. It depends on which direction you are going, like moving forward reaction or backward reaction. And same delta S will be equals to entropy of beta minus entropy of alpha, and then the delta G equal to free energy of beta minus free energy of alpha. A change in free energy. Now, what is this T? T is transformation temperature. Let's write it as TR. Okay? TR. What is my TR? It is transformation temperature. So when it is transforming, that is what we are writing. This transformation temperature. Right? So again, at equilibrium, when two phases are at equilibrium, their free energies are equal. That is logic, right? Because then only we will say two things are at equilibrium. Then delta G equals to 0. So what is that remind with? Delta H minus T transformation delta S. That should be equals to 0. When this thing happens, this happens only when you are talking about bulk. Okay, we are completely like removing the surface part. We are not even considering the surface part. And if we consider the surface part, then what happens? See, alpha has some surface energy, beta has some surface energy. Initially alpha has some surface area, beta also has some surface area. Okay. What is the change? Change is this guy. So that is the change. Now if I try to write it, so this should be 0 at equilibrium. Now should be this. And then I have here is that's it. And the transition will be equals to this whole term minus T bulk. Or if I change the minus signs, then you can write any way you want, because finally you will remain with this term. Now what does this term mean? This term depends upon area, right? Now area will depends upon the radius, the diameter, right? So then it is something. Let's say it depends upon a function f of right shape and size. Okay, the shape or whatever you want to define. Then it will depend upon t. Right? So it will depend upon the size. So what is happening? Now, if my size is very large, t tends to infinite, then it will be 0. Then my t transition will t bulk, it will be same. But when my t decreases, then it will have some significant term. Then you have to remove, so it will be less. That's all. You do not need to derive everything, right? So just by logical way of seeing, you can just say, yeah, this term depends upon this and this term depends on that. So you will get that. why the eutectic composition? I hope everyone knows the eutectic phase or eutectic composition. Eutectic point is nothing but when a liquid, so eutectic action, I can write it as eutectic transformation. So I can write eutectic transformation transformation can be written as when my liquid state is transforming into two solids, alpha and beta. Then I will call it as a eutectic transformation. Right? So please try to remember. So eutectic transformation is nothing but when a liquid phase transforms into two solid. So this is what we call as phase transformation. I mean eutectic phase transformation. Right, so my liquid phase will transform into two solid phases. So what is happening here? You can see my liquid phase was first here, then it came to here, then it came to here. So what is happening? So my eutectic point is shifting. Eutectic point is shifting. Why? Again the same, the surface properties. You can see the melting point is also decreasing for both what is chromium or calcium here. For both it is decreasing. And because of the melting point, the interaction also will change. And because of the change in interaction, you have a change in composition eutectic point. Okay, so want to, yeah, I hope I have like cleared all the part of I have cleared all thermodynamics part. If you have any doubts, you can just ask in between. So, or even ask after the class, after the session. So it's on you. Let's just give a brief recap of what we did. Okay. So first we started with the loss of thermodynamics, right? In which we have discussed first, second, and third law. First law is nothing but which tells about the work and energy conversion, and second law tells you that some part of energy is not available and that is going into the system and we cannot use it, and we defined it as the entropy, and entropy was like defined at a certain temperature, so we just write it as T delta S. So in third law for thermodynamics, again we discussed what do we call how. So we have defined the term entropy. Then after that we have to find the first and second law of thermodynamics, and then I hope I'm audible. Yeah. Okay. So and then we define for how do we define the free energy for anything. So how do you define my free energy equation? So free energy equation is we have defined many things. So first we took G minus Ts. From there we moved on to, we combined first law, we combined second law to finally get this, the measurable equation. Mostly people call it VdP minus SdT. So why it is a measurable equation? Because from this equation you cannot say, okay, how do you measure enthalpy, how do you measure entropy? That is a big thing, right? So it's not that easy to measure this kind of thing. So there is no enthalpy meter or entropy meter to measure. But we have dP, the change in pressure, and change in temperature. So change in temperature is given by thermometer, and the change in pressure is given by barometer. That's all. So that's why we mostly use this equation. This equation is we get from combining first law and second law. So yeah, I have explained this first law and second law, everything, this equation derivation in my previous session. So there is no need to worry about it. You can just go through it again. It's also very simple to derive. It's not very complex. Okay. And then we came to how our nanoparticles or nanomaterials change with what? Size. So how our melting point will change with respect to size. We have seen it, and then we also derived for the vapor pressure or the excess pressure of a curved surface, and then we have seen a cold centering. When the two particles are near to each other, they try to reduce the overall energy. So that's why they coalesce. And you get a cold centering. That is what happens. So yeah, that's all. And then we have discussed how our we have seen how our melting point will change, how our phase transformations also changes, just about, and then we have derived the Gibbs-Duhem equation, how this Gibbs-Duhem equation is very useful. We have even seen this. So that is all about the thermodynamics part. Okay. Now moving on to the instead of this, let's say, okay. So let's start with how do you form the nanoparticle? Okay. There are two ways to do it. There are two main ways. I mean, there are many ways, but we broadly categorize them into two different parts. Okay. So one is my top down, and another is my bottom. Okay, these two use normally, right? So in top down, what do we expect or what do we see? So for example, if I have a particle, let's say, see, in both the processes, my final goal, in both of this, my final goal is to form nanomaterial. Nanomaterial and nanoparticle, my final goal. Right, I do not care what happens in between them. So I want to find, then I want to form a nanomaterial. So that is our main goal. Right. So for that, what do we need to do? For that, we have different processes. We will come to them in just a few minutes. Okay. So yeah. Top down. So top down is nothing but, so finally my goal is nanomaterial. final goal is nanomaterial. What do you mean by top down? Top down is nothing but I will take a big particle which has a size of like 10 microns, not 10 microns, 10 mm or 1 centimeter, a particle of 1 centimeter. Then what I try to do is I try to break it. And make it in smaller forms or simpler forms. Then my final will be nanoparticles. So I have achieved it. Next, bottom up. Bottom up is nothing but I take even small atoms, like even smaller particles, smaller than nanoparticles, like atoms, okay, or ions. Then I combine them or make a reaction so that they combine or they coagulate to form again same nanoparticles. Right. So it's like a line. Whether I come from larger dimension to nano range or even smaller dimension to nano range. So larger dimension is like 1 mm, right? 1 mm or more than 1 mm or microns. Even smaller dimension is less than 1 nanometer. Or atomic clusters. Then I reach to nano range. What is nanoparticle? That's so top, down, or bottom. Sorry, this is bottom, up, bottom, up. So these are two like very easily understandable process. Okay, so and there are many ways of doing this. So let's start with now again we have to characterize them, right? So how we have characterized our nanomaterials? Characterize nanomaterials. How do you differentiate? How do you differentiate the nanomaterials? So that is the definition of this meaning, or the meaning of this line. Differentiate. Okay, so characterization. How do we? So we have 0 dimension, 1 dimension, 2 dimension, 3 dimension. I'm not going to explain them again because we have gone through it many times. So 0 dimension means all dimensions in nano range. Mostly clusters are buckyballs, fullerenes, and only 1 dimension in nano range. 2 dimension, 1 dimension not in nano range, and then I have 2 dimensions not in, write it more clearly, all dimensions in nano range, 1 dimension is not in nano range, 2 dimensions are not in nano range, again all 3 dimensions are not in. Now again people have little confusion with why, if 3 dimensions are not in nano range, then why do you call it as a nanomaterial? So even though my material is not in nano range, maybe the micro constraints in nano range. Right? For example, my grains can be nano crystalline. My grains are in nano range. then the whole material is made up of nanocrystalline grains, right? The whole material itself is a big bulk one, but my grains are in nanograins, so we cannot like overshadow that part. Okay, so that's all. Now let's start with how do you make zero-dimensional nanomaterials or nanoclusters. Mostly we call them as nanoclusters. So we start with how do you start doing the zero-dimensional nanomaterials? Okay. Now, so the first will be inert gas condensation. Right? Inert gas condensation. Again, there are many ways. So first, we are first discussing about the nanoclusters, right? How to zero-dimensional nanomaterials. So zero-dimensional nanomaterials are mostly nanoclusters and buckyballs. So fluids, you can call them as. So how do we make them? Nanoclusters are either, you can either make them by gas phase or liquid phase process. Okay, what do you mean by gas phase? So again, we start with gas phase. So let's take any, what do we call methane gas. Okay. And the best way to explain this is the inert gas condensation or inert gas expansion. Now liquid phase process also can be used to form nanoclusters, but they use mostly the surface forces to create nanoparticles. Right, and there are ultrasonication one, there is a sol gel method, and there is other self-assembly method. Okay, so let's starting with inert gas condensation. So it's nothing but what we do is we first take a material like inorganic material which is easy to vaporize. Okay. So let's take our inorganic material, then we heat it. Then it will evaporate. Right, so that's what we are trying to do. So, and when it is heated, it is heated inside a vacuum chamber. Okay, and then what we do is, see, this is my vacuum chamber. Let's say this is my, let me draw everything. Let's say this is my chamber. It is completely closed. It is completely closed. Now what I'm trying to do is, I'm trying to heat my material, my inorganic material. Okay, so my inorganic material will vaporize. I have fumes going upwards. Initially it is vacuum, right? So now what I'm trying to do is I'm trying to introduce some inert gas. Now I'm trying to reduce the inert gas, right? So next what happens? So this gas will carry these fumes upwards, right? So this inert gas carries the fumes upwards, and here I have a cool finger, a cold finger, mostly a metal. Now what does that do is, whatever the vapor particles are there, they condense here. Why? Because the melting point, see here it was heated. Whenever the fumes go upwards, the temperature drops because of this cold finger. And once they come near to the cold finger, and because the temperature is very low, they again will condense. And condense, they form solids. And these solids can be scraped off after this experiment. And you will, if you do the characterization technique, then you find these particles are nanoparticles. Okay, so the vapor cools rapidly, and if there is a supersaturation, it will get supersaturation to form the nanoparticles, and they will have size range of 2 to, and the size range will be 2 to 100 nanometers, which can be collected from here, the fingertip. How do you collect? You just scrape them out. They will come out. And even the alloy particles are also made. So how do you make alloy particles? You make alloy by melting like one metal A here and the same melting B here. Right? Melt A there and I melt B. Right, so both the fumes will get carried out. They will mix at some point here. So they will mix at some point here, and then they will get deposited. Okay, so like that we can form. And the main drawback, see, everything looks good, but the main drawback of this thing is these particles will again, why? Because of cold sintering. Because of cold sintering, they will again get attached. They again will get, you have a cluster formation. So why do it forms a cluster? Again, to reduce the surface area. Now again, how do you control this? You control this by maintaining a very good cold enough temperature so that they again do not mix. Yeah, you need to play with the process parameters. And then the next one is the inert gas expansion. So what do they mean by inert gas expansion? So inert gas expansion works on this Joule's expansion theory, right? So for example, let's say I have a pressure, a gas, which is at pressure P, volume V1, temperature T1. Okay, now I expanded it to pressure P2, volume V2, temperature T2. There is sudden expansion. Okay, it's not like slowly expanded. So there is a sudden expansion. So what happens now? Because the volume got increased, right? So let's say my pressure was kept same. Right? Then what is PV equals to nRT? This is our ideal law. Okay. Now, in Joule's expansion, what happens is because my pressure drops, volume increases, and there is this temperature now. Now, if you want to balance must decrease the temperature here because see V1 upon T1 equals to constant. And because V1 is increasing so much, pressure is not that much changing. So then T1 should decrease. And then only you can cancel out and it will become a constant again. So mathematically it is there, but again mathematically it is there. Then how do you explain this Joule's expansion, right? In terms of what do you call it? See, so this is the mathematical way. Now how do you define in more physical manner or more characteristically thing, right? So see, gas molecules are very closely packed. When the pressure is high, there is some interaction between the molecules even though they are very far apart. So in gases there is no symmetry, right? They are just moving around here and there. See, so there must be some interaction between them. Okay. There must be some interaction between, even though they are very far apart in gases, the atoms have some interaction. Now, when you try to compress them, so when I increase the pressure, it is at, let's say it is at 1 atmosphere. Now I am trying to increase my pressure to 10 atmospheres. So there is compression. So we are doing is compression. Now when I do the compression, they will come close. Even though they are big, they will come close. See, here and here, you can see there is a change in length, right? So they are coming close together. Now, what I'm trying to do is, and to push these atoms close together, you need to supply energy. Right? When you supply some energy is going to radiate as heat, right? Because of the friction or whatever the things there are. So some energy is going to be released in terms of heat. Now, what I'm trying to do is, let's say from 1 atmosphere to let's go to 0.1 atmosphere, or let's say I'm decreasing pressure. Okay, so let's say from 10 atmospheres to I'm going to 1 atmosphere. Right? Now what's happening? Now the thing that's going to happen is you are going to release that energy. Whatever the energy was there, you are going to release it. So whenever you try to release that energy, whenever the energy goes out, so whenever the energy goes out, like the internal energy, whenever the internal energy drops, and internal energy depends upon temperature. It is a function of temperature. Because NCV dt or delta T, NCV delta T. Whenever my UV goes down, delta U, changing internal energy goes down, temperature also will drop. drops. That is what happened. So when we try to expand the gas forcefully, when you do the sudden expansion, then my temperature drops. So the same theory is used here. Right? So simple. At first, I have a chamber, and in chamber I am trying to heat my material. And the material again forms fumes. Gas molecules. So these are my gas that has been vaporized. Now what I am trying to do is, so it is in a chamber. Okay. At first it is closed. Now what I am trying to do is, now I am trying to purge helium gas or any inert gas. Now whenever you are purging high pressure gas, simple, it will first carry away. Now what I am trying to do is, now I am trying to open it. See, again from the conversion or the Archimedes principle, you can take that also. So again, you can consider the conservation of mass or flow rate, anything you can take. So that tells me that V1 A1 will be equals to V2 A2. So whatever that is entering here, that must exit here. So initially I have V1 A1. So A1 is less than A2. And that means V1 should be greater than V2. So at first I have very high velocity and then I have very low velocity. So that means the volume that is entering here, it is compressed. But the volume here, it is very large. That means we are expanding the gas. So again, same, the Joule's expansion. Whenever you have an expansion of gas, sudden expansion of gas. Whenever you have sudden expansion of gas, temperature whenever we have the expansion of gas, the temperature drops. Why? Because the energy is being released. So whenever the energy is being released, the internal energy is being released, then you will have the decrease in temperature. Right? And that decrease in temperature will result in, again, these guys getting condensed. And they will form clusters, nanoparticles. That is what happened. Initially, I melt it, we get gas. This gas is forcefully forced through a nozzle, which results in sudden expansion. And because of sudden expansion, the temperature drops. When the temperature drops, they condense, and they condense. When they condense, they will form nanoparticles. So this is the theory behind nanoparticles, one-hit gas expansion. And there is another realm for this, that is the adiabatic expansion. Adiabatic expansion is nothing but there is no transfer of energy anywhere here, right? It's just we are giving energy and then we are just seeing what's happening. So that's why we call it as a Joule expansion, and another is called the adiabatic expansion. Yeah, and the adiabatic expansion of the gas leads to sudden cooling, causing the evaporated atoms or the fumes to get clusters. Right. Again the same. These clusters can like stick to each other and they will form agglomerates. Which can be controlled by our parameters. The next one is the somochemical process. Now, how do we do the somochemical process? Okay, so again, the basic theory behind this is, see, how do we differentiate a solid and liquid surface? Okay, or solid to gas surface. So whenever you have a liquid, let's say this is my liquid, okay? Instead of like doing this, I can just slide. This will be much more easier. Now, this is my liquid. So what's happening? What is happening here is, whenever you have a liquid, the atoms of the surface are at low energy, are at higher energies. So what they try to do is they try to escape from the surface, and they become gaseous. They become gas molecules. When they become gas molecules, gas exerts pressure, and that is 1 atmosphere in air. That is 1 atmosphere. The air exerts pressure on us, and which is the 1 atmosphere. Okay. So same, the gas will evaporate some gas. Whenever you put a liquid in a vacuum, the gas molecules will try to escape from the surface, and they start exerting pressure on the liquid, and that pressure is given as vapor pressure. And this vapor pressure is given as P naught, because it is a pure liquid, right? So if it is a pure liquid, then it is a P naught of A, liquid A. Okay. So liquid A. Okay. This is called as a vapor pressure of A. Now, see, so this vapor pressure will start increasing, and it will reach a critical value where the atoms, see, when the atoms try to escape from the liquid, they exert some pressure. That means they are colliding with liquid again. So some gas molecules may again will join with the liquid. Okay. So the first step, the first reaction is the particles whenever you put a liquid in a vacuum, first thing that happens is the liquid particles escape and become gas molecules. Second, these gas molecules starts putting pressure on liquid, and at some point some molecules, third, these molecules will again start hitting liquid. So the fourth thing that happens is some gas molecules will re-enter liquid. So at first, rate of evaporation is greater than rate of condensation, right? Because more and more particles are moving into gas, and after some point, or fourth, rate of evaporation will be equals to rate of condensation. That means my liquid and gas are at equilibrium. So when you zoom in the surface of any liquid surface which is kept in a vacuum, so this is what happens. After some point, after some time, t equals to like 1 hour or 2 hours, at the surface you can see some particles are evaporating. At the same time, the gas particles are condensing. That's why you see a constant liquid line or the interface between gas and liquid. Okay, if evaporation starts dominating, then let's say this is my container at 1, so R evaporation at 1, R evaporation will be equals to R condensation. At 2, R evaporation greater than R condensation. Then my liquid will start diminishing, more and more gas will form. Right, you will see the more and more liquid is getting evaporation. You will have more and more gas molecules. This liquid. What if the rate of condensation is greater than rate of evaporation? Then my liquid gas molecule is being, most of the gas molecules are being condensed. Right, so that is what we see. See, now the gas molecules are very less. Whenever you have an equilibrium, that means you see a constant surface even after some time. That means the rate of evaporation, condensation are at equilibrium, are equal. Now, so why I am trying to explain this is, whenever you create a vacuum, inside a liquid, or not inside a liquid, inside a container having a liquid, the molecules stick with this. Whenever I try to create a vacuum, inside a liquid, see inside a container, then my molecules, the water molecules will come out, or the molecules of this will form gas. That is what happens. That's why I took the trouble of explaining everything. So why, whenever you have low pressure above your surface, the liquid will start evaporating. So that's what we see here. Whenever you have some low pressure, then the molecules will come out. Air molecules which are trapped inside a liquid, they will come out, and also the molecules, the liquid molecules, they also will get evaporated. Now, what is the relation with this sonochemical process? See, the sonochemical is nothing but you create an ultrasound. So ultrasound is nothing but it's a mechanical wave. So mechanical wave composing of two cycles: compression, expansion. So it contains two cycles: compression cycle, expansion cycle, and these two will, rotate. These two will change places. First you will have compression, then you will have expansion, compression, expansion, compression, expansion. It's just a cycle like this. So pressure is positive here, it is negative. That means this compression, this is expansion, compression, expansion, compression. It will continue. Okay. So whenever we compress a liquid, nothing happens for that time. And whenever you try to expand, right? So let's say this is my liquid. Okay. Now whenever I try to expand it, try to expand my liquid, then what happens? So this is my first liquid, which was in a compressed state. Now if I try to expand it, right? So expansion. So whenever you try to expand any liquid, there will be creation of low pressure states, low pressure zones, or there will be creation of voids. Voids are nothing but empty space. So empty space is nothing but vacuum. So whenever there is a vacuum, so let me draw it big. Okay. This time. Whenever there is a expansion, then you will have a low pressure zones. So whenever you have low pressure zones like this, whenever you have low pressure zones, there will be a creation of voids. So whenever you have voids, then there is a formation of bubbles. Right? What do you mean bubble? Bubble is nothing but gas. So you have this gas molecules. So whenever you have an expansion, there is a formation of gas molecule. And again, whenever you have a compression, these gas molecules will combine. So at first, you have expansion. So it's at first you have expansion, which results in formation of space or void. Then there is an evaporation, which leads to gas formation. In turn, results in bubbles. And again, when you have compression, this bubble these bubbles will coalesce. Right. They will combine and form one big bubble. Whenever you have a big bubble, so once you have a big bubble, again when you compress it, it will burst. Why? Because there is build-up in pressure. Because all the gas molecules are like compressed, right? So they cannot handle high pressures, these bubbles. So the same happens when you try to just poke a bubble, it will burst. Why? Because you are applying pressure there. The same thing happens. Whenever you apply pressure, these bubbles will burst. And when they burst, they release high amount of energy. Which in turn rises the temperature to very large values. So at this part, at this zone, this wherever the bubble bursts, you have very high temperature. And that is called as hotspot. And there the temperature can reach like very high. And high temperatures can lead to evaporation, and this evaporation can lead to some reactions. So yeah, and these reactions will tend to form nanoparticles. See, you have pressure waves, you have reacting hotspots, the high temperature part, and because of the high temperature part, there is a formation of nanoparticles. That's it. Okay. Now, moving on to the next one, which is the you can call it as a sol gel deposition. Okay. So see, the hotspot can reach up to like 5,000 degrees centigrade. So the temperature goes that high at that old point. Whenever you have this bubble formation, and so temperature can reach up to 5,000 degrees centigrade. So that's why there will be formation of different reactions happening there. So yeah, let's not go very deep into it because in itself is big subject. So now moving on to sol gel process, or people even call it as sol gel deposition. So what happens in sol gel deposition? So in sol gel deposition, so what do we make from sol gel deposition? So we make ultra fine particles, nano thickness films, and nanoporous membranes can also be made from this sol gel process. So the starting point is the precursor, right? So starting point is precursors, and they are mostly metal oxalates or metal alkoxides solution. And now the precursors can be dispersed in a solution, mostly inorganic solutions, solvents. We call it as solvents. Solvents instead of writing solution. So they are dispersed in solvent. These precursors are dispersed or immersed in solvent. Solvents can be inorganic solvents. Okay. And again, the precursors can be usually inorganic metal salts or metal organic compounds or metal alkoxides or metal ions with organic ligands. There can be anything for precursors. Okay, it depends upon what you are trying to make. The precursor is subjected to, and then the precursor is subjected to polymerization reaction to form colloidal suspension. Okay, so whatever first I have a solvent, and then I add precursor, and then what we try to do is we make them to have polymerization. Polymerization is nothing but attaching molecules to other molecules. Right? It can in this way, it can in this way, it can in any way. So that is what I mean. Once you have a precursor in a solvent, and then you make the polymerization. Okay. So and then you have a suspension. Once you form the polymerization, you have a suspension, which is called as a salt. That means the discrete, finely dispersed particles kept in suspension by adding surfactant. So what does the surfactant do? So see, first I have a solvent, and then I add precursors. Precursors will agglomerate or do the polymerization, and they form particles. At first I have everything clean solution, right? The solvent in which we have precursors, and then we do the polymerization, then we form a particles. Okay. Now once we form the particles, we should make sure they do not attach. So for that to happen, we modify the surface by adding surfactants. So what the surfactants do? Surfactants has one end hydrophobic, another end hydrophilic, or any other thing. Okay, so maybe positive and negative end. So one end is getting attracted to nanoparticle. Now, and because the ends are hydrophilic or the same charge type, they repel each other. So that's why you have a fine dispersion of a very good dispersion of these solid particles, of these particles, okay, nanoparticles, finely dispersed nanoparticles. And then what we do is, so yeah, you have your nanoparticles. We can even modify them. How? Let's see. So the modification is done by adding the surfactant emulsion. Okay, so whenever you add the surfactant emulsifiers, what they do is they just take out this surfactant, or they take out this part. Then you have the particles which starts attracting to each other or agglomerate. Start agglomeration. So once they start agglomeration, you will find more or less like a chain of molecules. Or more or less a porous medium. Okay? See, they start getting attracted to each other and they form agglomerates. So once they form agglomerates, you have a network, a network-like structure. Right. So whenever you have a network-like structure, now after that, what you do is you dry it. So whenever you dry it, the liquid inside this structure is the liquid. So the liquid inside the structure will start evaporating. So the liquid inside the structure will start evaporating. once you have this operation done, then you have very porous structure. Very porous, right? So just like here. So once the gel, whatever the liquid inside the particles starts evaporating, then you have a nanoporous membrane, right? Because wherever the gaps where the liquid was present, though the liquid gets evaporated, then you finally remain with nanoporous membrane. And these can be used as the plugs for the solvent purification and for many other things. See, the solvent methods are very basis for a wide variety of materials. So these solvent methods can be used in making paints or the emulsifiers, we call it as emulsifiers, and in making porous ceramics and porous ceramic structures. So we use it in plugs, fuel plugs. Okay, and then they can be also used in the ceramic. So ceramics is completed, right? So, and then cosmetics, and also in few detergents, and very few are used in fuel cells because of the catalysis thing. Okay, so because of this porous structure, the catalytic, for catalysis you need the high surface area, I mean large surface area, so that can be provided from this porous structure. Okay, so that is about this. And then coming to, so whatever the process we have discussed, they are used for the production of zero-dimensional nanomaterials. Okay. So now we are starting to moving on to the production of one-dimensional and two-dimensional nanomaterials. Right. So now, so in one-dimensional nanomaterials, again, like 1D and so one-dimensional nanomaterials, one dimension is not in nanoscale. So there can be CNTs or graphene, not graphene. Graphene is a two-dimensional material. So CNTs, multi-bond CNTs, single-bond CNTs, nanorods. So these are all one-dimensional nanomaterials. And in two-dimension, we mostly see graphene sheets, or gold, very thin gold layer. Right, and glass planes, and many more. Okay, so yeah, it is simple. So what we do is we first have a precursor material, right? So let's say this is my precursor material. So what I'm trying to do is, so let's, for example, if I form a solution, so if I want to deposit something onto it, let's say my surface is very hydrophilic, okay? Surface is hydrophilic. Now what I'm trying to do is, see, let's say this is a polymer chain, okay? So this is my head, and this is my tail. So my head is hydrophilic in nature and my tail is in hydrophobic in nature. So that's why they are inverted, right? So head is attracted towards the liquid but not the tail. Whenever you just strip precursor from a solution, then they will start adhering to this surface because of the nature of the surface. Okay. Now, yeah, there are many ways. Again, same. You can form a nanoparticle and then you start using a better surfactant depending upon the property, and then you have fine dispersion of these nanoparticles. So that is, in most of the cases, we stabilize the nanoparticles by dispersion. Using surfactants. Even we can use, for example, for stabilizing Fe3O4 nanoparticles, we can even use some polymers, or we can even use acetic acid. And it is easier to like stabilize Fe3O4 compared to other particles. Right? People have used acetic acid and yeah, many other things. We can use chitosan to stabilize the Fe3O4 nanoparticles. Okay? So, and then you have the electrodeposition. Right? So the electrodeposition is nothing but we have a solution. So let's I have a solution with ions. Let's say Cu plus 2 ions. And then at one side I have pure copper electron. Okay. And then here I have inert electron or platinum electron. This is my pure. So let's say this is my copper sulfate solution. Okay. Now this is my pure copper. Then this copper will get deposited because we are supplying electrons. Right, so we are supplying electrons here. And these copper plus 2 ions need electrons to get deposited. So that's how I will have clusters. And if you still supply the electricity, they will start growing. And you will have a lamellar, not lamellar, yeah, you will have a lamellar growth. Or you still see, and this you can form nanorods. So if you do not if you continuously supply the electricity or if you continuously supply the electrons, then you will finally end up with So if you continuously supply the electricity, these will grow. Whatever the spots first form, they will grow. Okay, and they will mostly look like rods. Because the copper starts depositing on the same top. Now, if I want to form a thin film, right, then what I need to do is thing I need to do is give a pulse. Right? We want to stop the motion of this thing, right? We want to stop the motion of this columnar precipitates. So for that we need to give pulse voltage or pulse current. Right, such that I only form precipitates here. And again when you give same amount of pulse, then they will. So the growth happens the layer by layer. And we have to give very high amount of voltage so that there will be no gaps like this. Without gap, if you want to form a film, then you need to give a large amount of voltage but in a pulsing manner. Then only it will grow layer by layer. Then we'll have a filament. Right. So yeah. And this is also very dangerous, right? Because whenever these outgrow their size, they can short the circuit, which can even lead to an explosion. So this is the main cause for some of the batteries where we use liquid, right? Lead sulfate batteries, lead batteries, where we use acids, right? And whenever we continuously supply some amount of energy, some amount of direct current, then there will be this lamellar growth of lead on one plate. And once they reach certain size, they will short the circuit, which results in explosion of batteries. Yeah, which is mitigated right now, but it was one drawback of this liquid type batteries that we use. And now most of the cases now we are using solid state batteries. So yeah, and we have physical network deposition. This will be discussed in next few lectures. Okay, so next session we will discuss this part. And yeah, again, this is the most crude way of making sheets. You just beat down the gold layer until you find minimum thickness, right? So a very thin foil can be made by just hammering the gold, right? Because the gold is easily moldable, right? It is easily deformable when compared to iron or any other metals. So yeah, even copper can be done like this, but gold can be easily done compared to other metals. And the other one is the extrusion part. Let's say you have a grains of some size, let's say 0.1 micrometer. Let's say this 0.2 micrometer. Now what I'm trying to do is, let's say this is my material, cylindrical material or any type of, any shape, point of which is made up of these grains. Now what I'm trying to do is, now I want to make this as a nanomaterial, 3-dimensional nanomaterial. That means my microconstituents are grains in. So these grains should be in nano range. So for that, I need to reduce this size. So how do I reduce this size? I extrude it, right? So if I want to reduce the thickness, I may elongate this part, right? So if I have a particle like this, and if I want to reduce this dimension, I can like increase this part, I can increase this dimension, then the conservation of mass will kick in and it will become, it's all about the material flowability, okay? So this will become, now it is in 0.01 or 100 nanometers, right? Because 1 micrometer will be equal to 0.01. same thing is happening. Initially I have a good amount of grain size, and once I do the extrusion, it's just extrusion is nothing but you have a small orifice, and from there you try to like deform your material and just push it through this orifice. Okay, so that is what we do in extrusion. We extrude the material from a small orifice or a nozzle, right, in a defined shape. So that's how our steel rods are being made, right? Some copper rods. So initially they have very large diameter, and they kept I mean, they are forced into a die which has a larger diameter at first and a smaller diameter at last. Right, so the copper wire, so the copper rods. This is my initial part. Extrusion is one of the metal forming process. So initially I have this rod. Which are forcefully drawn out, right, through an orifice. So there is a decrease in this diameter size. And this is one of the metal forming process, and there are many things in it, right? If I do not like, if I put it like this, and if I am like drawing hot metal, then I have this dead zones and many things. It is one of the type of metal forming process, so let's not go deep into it. Yeah, so from this you can like deform or change the texture of the grains. Okay, how they are oriented, the size can be varied, right? So yeah, so that's all for today's session. If you have any doubts, you can ask now, or you can like end the meeting, right? So thank you.